Bismillahirrahmanirrahim. Starting with the name of Allah, who is the most merciful and beneficent. Here I am Aqeel Rehman from Civil Engineering Department, UET Peshawar, presenting conference paper with topic Load Contribution of Basement Wall in Piled-Raft Foundation, and first international conference on advances in civil and earthquake engineering 2021. Here are the authors Aqeel Rehman, Aqib Ahmad Asmatullah, Mr. Irfan Jamil and Mr. Waliullah. First of all, the introduction. Nowadays, population increase and urbanization is major problem worldwide, and everyone wants to have the tall buildings to use the land effectively for the residential and commercial purposes. We know that tall buildings have multiple basements, at least 2 to 3 basements for parking and storage facilities. In tall building, major forces is lateral forces such as earthquake and wind forces, which are mostly the governing design criteria for the foundation or the structures. But conventionally, basement is not considered to resist these lateral forces and only designed for soil backfill pressure, which ultimately leads to uneconomical foundation. In practice, basement shows resistance to load, especially in resisting lateral load induced due to earthquake and wind. Many researchers work experimentally and numerically on the lateral response of Piled-Raft foundation. They summed up that raft and piles both contribute to the lateral load resistance. However, the current literature lacks the study on the basement walls. A real study has been achieved on the basement wall contribution in tall buildings foundation. There are many buildings which have Piled-Raft foundation and basement wall, as shown here. The Brookliner in New York, Massatorhus building in Frankfurt, Burj Khalifa in Dubai, the world's tallest building. The question arises to how basement can provide the resistance to the lateral load. For this, Harry Paulus and Harry Chow gave 3 reasons in their conference paper, and they said that shear resistance along the sides of the basement walls, passive resistance of the soil in front of the basement wall bearing, and shear resistance at the base of raft slab provide additional stiffness and resistance to the structural loads. Here are some of the conclusions from the Harry Paulus and Henry Chow conference paper, and from these figures we can clearly see that the capacity and the system stiffness of the Piled-Raft increases as the depth of the basement wall increases. This slide shows the hypothesis which we assumed before we done our numerical study. For instance, if we applied total lateral load of 5 tons, then in case of basement wall with Piled-Raft foundation, all of the load will be distributed among each component. But in case of pile foundation, each pile takes 2.5 tons and all the load is transferred to the piles. From the aforementioned review, we mentioned 2 objectives: to understand the response of basement wall under lateral loadings, to compare results of Piled-Raft, pile group and Piled-Raft with basement walls in terms of deflections and load contribution of each component. For the numerical modeling, we use Fluxys 3D, a finite element analysis program. In Fluxys 3D, there are different models for the soil, such as Mohr-Coulomb model, linear elastic model, but we use the hardening soil model as it is more advanced and it is able to generate more realistic soil response. The properties are mentioned in the table about the soils. The drainage type we mention as drain, because we use sand soil for our analysis. Also, the Poisson ratio cohesion is 0 for the sand. Angle of internal friction from direct shear test is 34 degree. Unit weight are also determined, which is 96 pound per cubic foot. The most important input parameters are given in this table. Firstly, we have to define the stiffness parameters. First one is secant stiffness modulus, automatic stiffness modulus, and unloading reloading stiffness modulus. Secondly, we have to define the strength parameter, which is cohesion for the sand is 0, angle of internal friction from direct shear test is 34, dilatancy angle is 4 degree from the equation, which is 5 minus 30, and the interface factor, which is 0.71. The most important of these parameters is sequence stiffness modulus, which was determined by using the triaxial test, CD consolidated strain test under cell pressure of 30 kPa. And from the graph axial strain versus deviatrix test, we can find the stiffness modulus, which is 17.5 megapascal. And using different equations, we can also find the volumetric and unloading reloading stiffness modulus. Direct shear test is shown in the above figure, and by this we can find the cohesion angle of internal friction and interface friction angle. The basement wall and raft were created as plate elements, and properties were assigned as shown in this table. Raft and basement wall material was aluminum. Material type for both is elastic, and model type for both raft and basement wall is plate element. Piles were created as line element embedded beams, and the properties were assigned as shown in this table. Galvanized iron for the material, elastic for the material type, and model type is line element. Median meshing was used for the analysis because we have to reduce the time for the analysis and to easily run the analysis. There we comes up with the results for the 2x2 pile configuration. Pile group, Piled-Raft with basement wall. From the figure, it is quite clear that due to basement wall, displacement reduced significantly because of the increased stiffness of the basement wall. For 0.5 mm displacement, pile group resists only 150 Newton, and Piled-Raft sustained up to 500 Newton, while 2700 Newton lateral load was required for 0.5 mm displacement in basement wall with Piled-Raft. So by this we can conclude that due to basement wall, the overall foundation stiffness increased. This table shows the contribution of each component in each model type. For pile group, 100% of the load is transferred to the piles. In Piled-Raft, 39% load is resisted by the raft, 61% is transferred to the piles. In basement wall with Piled-Raft, 20% resisted by the piles and 80% resisted by the combined raft and basement wall. So using this research study, we can reduce the number of piles, or we can reduce the dimensions of the piles. It also shows that the resistance to the lateral load that may induce due to earthquake or windfall is also resisted by the basement wall. From above results and discussion, it is concluded that basement wall increased the stiffness of foundation by reducing the displacement, and 80% of lateral load is also resisted by the basement wall and raft, and only 20% is transferred to the piles. By considering this research study in foundation design, we can make our foundation economical by reducing the number of piles or its dimension. Here the references are given. Thank you for listening.